Okay, so earlier we went through and explained what all of this is. That got to be a little long. I'll see if I can try to keep this part quick. So now we're going to go through and take a look at example A and example B down below. Now you'll notice this is two different examples. They're linked. They have the same, or they're using similar information, and they are about this free body diagram, about this force, about these interactions on this box. So when I go down here, example A, we're saying that the force of tension that the rope exerts on the block is 20 newtons, and the force of friction that the table exerts on the block is a negative 10 newtons. Find the total force on the block. So this first space is a space to put the data for this problem. That is really tremendously helpful. That's a step that most beginners want to skip, but most people that are practiced in what they're doing do. So generally the people that know more use this step. So I encourage you to do that. That just is a form that'll help you get things taken care of sooner. So we have this data here, and now plan your solution. And I'm trying to find the total force. I'm trying to find the sum of the forces on the block. I really probably should say here in the x direction. That would help. So as we go through and we look at this problem, we're saying 20 newtons for the rope on the block, negative 10 newtons for the force of friction. So when we go up here, we're saying this force is 20 newtons, this force is 10 newtons, and it's in the negative direction. So of these relationships to find total force, we really have these two options, this row or that row. And remember this row, these two equations are the same thing. So when I go down here, the equation that's probably most useful is this one. We can go through and we can use the sum of the forces on the object. And so the sum of the forces on the block in the x direction is, the tension rope on the block plus friction table on the block. There, made it a little bigger. Hopefully that helps. So the sum of the forces is this force plus this force. Now, it's always the sum of the forces. It's possible that some of the forces are negative, so they would end up acting in different directions. So that's planning my solution, is putting down the relationship, the mathematical relationship I'm going to use. Execute the plan, plug in the numbers with units of measurement. I want to make sure we do that, adding the units of measure or including the units of measure, because otherwise we quickly forget that this is dealing with physics things. This is dealing with pushes and pulls and objects and accelerations and velocities. As soon as we stop using those symbols or the units of measure, as soon as we stop using newtons, it becomes just a math problem, quickly in our head at least, right? And we start to forget the physics meaning of what's going on. And so if we keep the newtons marked down in there, that helps us in our head remember that we're talking about pushes and pulls. And I believe that's very important. So here we have the sum of the forces. Again, I should probably have that there. Sum of the forces on the block in the x direction is 20 newtons plus a negative 10. And then stating our answer, that's executing the plan. That's using the relationship that we've got. And then stating the answer for what we've got. I just end up adding those things up, and I get positive 20 plus a negative 10 gives me an answer of 10 newtons. So that's the solution for that part of this problem. The next question, example B, actually links example A, and that's how the first 6 questions on this sheet go. Example 1 and 2 linked. Examples 3 and 4 linked. So the same thing here. Example A and B are connected together. Example B says, if the object has a mass of 10 kilograms, what is the acceleration? So now we're saying we're still using this data, 20 newtons, negative 10 newtons, but now we're adding in the mass of the object is 10 kilograms. And in addition to that, we're using the sum of the forces as 10 newtons. We did that in example A. We're sticking with that. That's still true. So now, plan your solution. We want to find the acceleration. Now, we can go up to these relationships. And the truth is, all of these are using, well, one exception. All of these are using the same equation, just rearranged algebraically. So any one of these could be rearranged and solved for acceleration. In our situation this year, I thought it'd probably be easiest to just include those that have acceleration already solved for them. So these three relationships all solve for acceleration, and any one of those, they're all identical. Any one of those could be used when we're trying to solve this question. So when I go down to example B, and again, we're talking about this block with the forces acting on them as stated here. So when I talk about planning the solution here, I would probably end up going, well, this is the start of that relationship. So this is the beginning of this relationship solving for total force. But we want to solve for acceleration. So if we rearrange this, we get acceleration in the x direction is the total force on that block in the x direction divided by mass. So this is planning out the solution, solving for acceleration in the x direction, execute the plan. So now if this is the relationship I'm using, I can plug in these values. And remember that then we're using the information. Question A and B are linked, just like in a minute, question 1, question 2 will be linked for you. So we already know the total force is 10 newtons. So when I say this, the acceleration is the sum of the forces divided by mass, I can say acceleration is 10 newtons divided by 10 kilograms. So now when I go over to state my answer, I can just say, hey, when I divide 10 newtons by 10 kilograms, I get 1 Newton per kilogram. So a Newton is a measure of force, a kilogram is a measure of mass. When we go through, if we simplify that or make it written down in a different set of units, it's also possible to say acceleration is 1 meter per second per second. That means that if the acceleration is 1 meter per second, that means that the velocity changes by 1 meter per second every second it moves. So if it starts out going 0 meters per second, 1 second later it'd be going 1 meter per second. A second later, 2 meters per second. 1 second later, it's 3 meters per second. And it just gradually speeds up as it goes. So that's the way these accelerations work. So now we have example A and B are demonstrated and shown. They're both dealing with this block, with this setup. Questions 1 through 6 work in very similar fashions. They all deal with this block, with this setup. So question 1 and 2 are linked together. You use them as though they're kind of like 2 different parts. It's kind of like question, the first question part A, first question part B. And then 3 and 4 are kind of like second question part A, second question part B. And the thing to be aware of, this question is asking us to solve for acceleration. They give us the mass. Some of these other questions say, hey, here's the mass, find the acceleration. But then this one says, here's the acceleration, find the mass. So when you get to these, you have to make sure that you're being careful that you don't do all of them using this equation. That's only if we're trying to solve for acceleration. If you're solving for mass, then you're probably going to want to use one of this equation. All right. When you're done with this question or with this worksheet, you can check. I'll have the answers posted on the bottom of the, or I'll have the answers posted either on the bottom of the sheet or linked in the assignment text. So you can check to see what you got. They might not be in the proper order. I'm just going to have a bit of answers there, and you can check to see if your answer, if your solution is there. Good luck, folks. Send me an email if you have any questions. There you go. Have a good one.